All right. Okay. So what we just got done covering was, a fairly basic example. We looked at the difference between energy and power, saw how they're related with time. So let's back up just even a little bit further and start with the three laws of thermodynamics. And I'll describe them the way I like to remember them. And they're cleverly named the first, second, and third laws. So,
You don't have to remember any names.
yeah, and then there's a few ways to remember it. There's a few ways to remember it. So the first law, second law, and the third law. And I'll write it in mathematics first. The first law just says that the change in energy, so delta just means change. And you can think of that in the change in your bank account, right? So if delta is positive, it just went up. If delta is negative, it went down. So the change in energy divided by the change in time, so as we move through time, that's just zero. And so it just says that energy cannot be created or destroyed. We'll see more of that later when we talk about the different types of energy that you use in a home. The second law says that the change in entropy is, over the change in time, is greater than zero. What's entropy? When I first walked in this morning, Sean and I were talking about the difference between a Stirling engine and a combustion engine, et cetera, et cetera. Any engine, any motor, any machine has to have some energy flowing into it. In terms of a combustion engine, or even the boiler or the furnace, what have you in your house, takes some kind of heat flowing into it. We'll get more to this later, but in general, the symbol that's used for heat in physics and in engineering and in the building trades is Q. Don't ask me why. You could all another way to write. You could think of it as this: is just energy sub heat. So Q is thermal energy. Now, entropy. See if I can squeeze this thing in here a little bit somewhere. Entropy, any change in entropy equals the change in heat. So think about you wake up in the morning, throw some wood on your log. What's I'm going to call it first? It's just your wood stove, wood burning stove. You throw it in there. Heat is released. Your house was at some temperature, and the whole idea is to get the house warmer, right? Now, when you do that, when you change the thermal energy, the Q inside the house, that's happening at some temperature. Wherever you like it. I don't know, like at 48 Fahrenheit, some people like it 80, whatever. So entropy is something you can measure. And it's it's just measured like so. It's just joules, and we already realized that joules is a type of energy. You can use calories or whatever you. It's just joules per Kelvin. And what that means is that anytime energy is transferred, the universe becomes more disordered. And so, what do you mean by that? Well, all the smoke, the soot, the ash, the CO2 comes out of the wood-burning stove, and you don't really want to breathe it. It's disordered. The universe has become more disordered. If you want to dig into this more, I've had a lot of my energy tech students look at it, and I can put this in the shell. But it's basically saying that right now we as a global civilization and any other living organism on this planet is always consuming energy. We have to eat to survive. We have to burn wood to stay warm. We have to put gas in our cars to move. The tricky, subtle thing is, I just told you, or the first law just told you, that the amount of energy in the universe can't go up or down. It's always the same. What it can do is change forms. So in the case of the wood combustion I just gave, you're just changing chemical energy into thermal energy, right? That's the whole point of it. The same thing with the electricity that we were doing. We were changing, well, it was chemical if it was, coal burning at the coal-fired power plant. It might have been mechanical if it was flowing through the wind turbine. It might have even been solar if it was flowing through your PV. All of that electricity then becomes electrical energy. In the case of the lights that we're using right now, the computer, that again becomes electromagnetic energy. But at the end of the day, it all becomes thermal. Like the prediction is that at the end of the universe, everything's going to be everywhere and the whole dang thing's going to be the same temperature. We've got a long time before that happens, but that's kind of the point of this video, and I'm not going to waste lecture time on it, but if you're kicking around on YouTube or bored with your Netflix, watch this video. It's just a... Are you going to put it in Moodle? I can put it in Moodle, yeah, cool. I will. We'll take a look at that. Okay, so that's the first law. Can't create or destroy energy, only change the form that it's in. Second law says that entropy increases no matter what you do. The third law just says that the temperature of wherever you are is always greater than zero. So there's a lot of, I'm not sure if you've ever gone to the hospital and had to have like an MRI done, magnetic resonance imaging. Those magnets have to be very cold in order for the helium that's flowing through there to remain liquid. But the point is, you can never get all the way down to absolute zero. Absolute zero is negative 273 Celsius. It's 0 Kelvin. It's negative 500 something Rankine or Fahrenheit. Anyway, the point is, heat is always trying to leak from some place to somewhere else. So no matter how hard you try to make the temperature zero somewhere else, there's always going to be some heat that invades your little experiment. So those are the three laws. And written in English is, I like this. And I can't remember who coined it, but it's just you can't win. So you're not going to walk away from Vegas with more money than you walked into. Or it's just on average. Well, some person might, but someone else isn't. And, this one is you can't break even. So that the house will always win. If it didn't, it would go under and you wouldn't get to gamble anymore. You can't break even. And then this one is you can't stop playing. So, you can keep trying to get to absolute zero, but you can never get there. Can't stop playing. Okay, so those are the, really the three, in my mind, three fundamental laws of classical physics. We're not going to need to get into quantum and all that kind of thing and building energy efficiency. But if you know that you can't create or destroy energy, so when you're adding up all the different energies, thermal, chemical, electric, it better come out to zero. It's not going to come from nowhere. Just keep looking until you find it. You also know that entropy is increasing. And I have written a little bit on this paper. The energy tech students have written it, and I've actually tried to quantify how much entropy different systems make. And what I've also tried to do is say, well, if more and more disorder occurs, then there can sort of be some backlashes from that. And some people even think that climate change is entropy accumulation in the atmosphere. And then the third law is not quite as applicable, but it'll come into play later. Okay, now let's look a little deeper at power now. How are we doing on time? Perfect. Okay, so let's take another look at power. And what I want to do is show two or three different types that are going to be important here. So in a mechanical system, what are you going to multiply by what to get power? Think of some mechanical system, car, a pump, a fan. What are you going to multiply by what to get power? Let's just start with a car first of all. So here's your car. So artistic. There it is.
Is that the Prius that cannot run the cops?
I'm not sure. It looks like it's been in an accident. So every one of these things we're going to come up with power. What's going on? What's one thing you know about your car if you're driving down the road? What's one thing you can tell me about it? It's got some friction, but even more simple. You look at the dashboard. What are you going to tell me? What's it going to running? How fast is it going? Yeah, there you go. You look at the gauge. What's my speedometer? And we're just going to call that velocity. What's the thing that's happening to the car all the time that you can feel but you can't see, right? You stick your hand out the window, what are you going to feel there? Yeah, some resistance. You're going to feel some kind of force, right? So in the case of a linear mechanical system, power is just force times velocity. So in this case, the car's moving forward with some velocity, and it's pushing against the road. One thing I didn't cover, but one of Newton's laws is that forces are equal and opposite. So however hard the car is pushing on the road with some force, the road is also pushing on the car. And it's doing that to push air out of the way. Someone mentioned resistance. There's resistance and friction inside the engine. So in a linear mechanical system, you've got force times velocity to get power. I heard somebody say torque earlier. Torque is applicable in a rotational system. So let's do this. And this is going to be for like the compressor in your refrigerator, your air compressor, that fan back there in the corner. What's going on? Camshaft in the automobile, absolutely. What's going on in there? I'm just going to draw a little fan here, and you can think of this as either having a motor, or you could think of it as being a generator. We know the thing is spinning, and I'm just going to call, and again, the nice thing in all of these cases is we're getting back to power. Why do we care about power? Because we're going to multiply it by time, we're going to get energy, and we're going to pay somebody for it down the road. And so at the end of the day, all of this, the bottom line is still going to be money in every single one of these deals. So that's why we care. Okay. In this mechanical system, you've got two things going on. Somebody already mentioned torque. If you've been out to the shop, you can go pick up a torque wrench. That's just measured in foot-pounds or Newton meters or whatever. As it turns out, torque, and I've written that as kind of a funny-looking T. That's a Greek letter tau. It's just a capital T with a little bend at the bottom, or a lowercase t that doesn't stick out the top, however you want to think about it, but that's a tau. And there's some, torque on that fan, on that motor, on that generator. It's also spinning. With some omega. And omega is, again, just a Greek letter, looks like a W. And they're similar, right? We know that force, well, let's write it like this. We know that force is measured in either newtons or pounds, LBS, and we know that velocity is always measured in miles per hour, or meters per second. Down here, as I mentioned previously, torque is measured in either Newton meters or foot-pounds, and angular velocity is just measured in hertz, or in hertz is just 1 divided by seconds. Nice thing about all of these is when you multiply them together, you still get power. Power is power. You can measure in horsepower, you can measure in watts, but it's just one thing. It's just power. Okay. Now, the next one I want to mention is just, so these are both mechanical systems. This one is a linear mechanical system, and this one is a rotational. If you can think of another type, let me know. There's only two kinds I know of. Things either go back and forth or they spin, or maybe some combination of the two. The next one is just a battery, or we were talking earlier about outlets. So what's going on in your battery system? Well, you're going to measure this thing. If it's a car battery, it's 12 volts. If it's a handheld battery, it's 1.5. And there's all different shapes and sizes. But you're going to put your multimeter across this, and you're going to get some voltage. Now, why do you want the voltage? Well, that's going to help push electrons through your system, fridge, lights, stereo, what have you, and that system is just going to be some resistor. Here it is. Electrons are coming out here, flowing through there, going through here, coming back in there. That is the fundamental basis of any electrical system. Now, what do we multiply by what to get power in an electrical system? I already mentioned volts. Watts are what we're going to get out when we multiply the two things together. So this is a big V for volts. This thing up here was a little v for velocity. Yeah, even simpler though. What's flowing through this thing? Yeah, current. And that's typically written as I. Sometimes you might see it as A, but A is the units. Current is measured in amps. I is the variable used for current. So P equals VI. Okay. Now.
Is it EI squared?
No. But I'll tell you what you're thinking there in a second.
I'm thinking higher.
Yeah, I'll tell you we'll go there in a little bit with the I squared, yeah. Now, here's the big picture on power. This is going to be true in the two mechanical systems I just mentioned. It's true in the electrical system. It's going to be true in a hydraulic system. So if you're out here looking at your heavy equipment, it's going to be true in your thermal system as well. And I'll write those out in a second. But before we get too out of hand, the way I want you to think about this is that these three variables, force, torque, and voltage, are what are known as across variables. Because force, and I'll just do a little hand puppetry here, force is felt across space, right? So if you've got a tug of war going, one side's pulling here, one side's pulling here, that force is transmitted across space. And nothing's moving. It's just there in space. Same thing with torque. You can be honking on that torque wrench, and whatever's going on at your hand is also going on at the lug nut. So that torque is felt across space even though nothing's really moving. Same thing with voltage. You got your cathode, your anode. That voltage is there. It's also sitting, right here in the outlet behind me. Nothing's moving, but it's a potential across space. Okay, so that's why it's called the across variable. You can think of it as a potential variable, but the formal word is across. Not a very fancy one. Let's see, 2 syllables.
Yes, I believe that is a 2-syllable word.
Okay. So velocity, angular velocity, and current are all through variables. So when you think of velocity or you see velocity, that car is moving through space. When you think of rotation, that turbine or fan is spinning around through space. When you look at that current, even though you can't see them, those electrons are flowing through the wire. So in every single case, when you're doing power, you're going to multiply some across variable by some through variable. This is going to be the same deal when we're doing our blower door later. And let's just look at that while we're talking about it. So let's just do, and I think next week we're going to do fluid mechanics. So we're skipping ahead just a little bit. But in the case of a HVAC system, what you're going to have here, and there's two separate things. First one we'll just do fluid, and here we'll do heat. Kind of the neat thing about this is that the flowing fluid itself has mechanical energy. Right? You know, it takes energy to move a fluid. The heat in that fluid is also flowing energy, but it's more or less taking something that's hot and moving it towards something that's cold. And yeah, how do we want to write that? Well, let's just write it like this. Let me get too crazy here. Let's write it like this. Power, in the case of the fluid, well, there's a couple different ways to write this, but let's just think of it as the more or less the pressure. So again, the pressure is your across variable, right? So you're going to have high pressure on one end, low pressure on the other, and then and this is where it gets a little wonky with the numbers. I'm just going to write this for now as Q. Q is the mass flow rate, so I'll define those. So P equals pressure. So that's how hard the fluid is pushing. And then Q, for now anyway, is the mass flow rate. I'll see if there's a different variable in your book we can use, but for now let's just use Q. So mass flow rate. Okay, so again, think of it this way. The more pressure you have and the faster the fluid is flowing, the more fluid power that's flowing through the system. No surprise there. Same thing here. Power equals, and in this case, it's just going to be the enthalpy, and I'll define what enthalpy is shortly. And again, times the mass flow rate. In this case, I'm going to draw it a little bit differently, and I'm just going to write it like so. M dot. In fact, just to avoid confusion, if you don't mind, let's just back up one quick second, and I'll just use the same symbol. I'm trying to figure out which level to confuse you with. I think this is the lesser of two evils. So just M dot. M dot. Okay, so in this case, H equals enthalpy, and M dot, we'll skip the Q for now, equals mass flow rate. And the way to think about the mass flow rate is just if you were to put a colored dye in your fluid, you might see it right here. A little bit later, it would be here, but it's just flowing through the system.
I think the book uses CFM.
Yeah. Okay. CFM is going to be the CFM is actually the volumetric flow rate, and we can go back and forth between volumetric flow rate and mass flow rate as well. But yeah, it's a good point. So again, the pressure is the across variable. Mass flow rate is flowing through, and you can think of that as your electrons, your car actually moving. Same thing with heat. Enthalpy is how much heat energy there is per unit mass. So the hotter the thing is, the more thermal energy it has, the more enthalpy it has, and the faster it's flowing, That's just m dot. The faster it's flowing, the more power it has. Like, turn up the heat. So there's a couple different ways. You can bring a whole lot of hot matter into the room at once, or you can bring a lot of warm matter into the room faster. So you can bring a hot thing in kind of quickly and just leave it there for a long time, or just keep pumping warmer air through. But in both cases, you're talking about power. Okay, so just to review what we just went over. Starting off with the first law, you cannot create or destroy energy, only change its form. Important thing to note is that typically heat wins the day. Once you turn something into heat, it's pretty hard to turn it into something else, unless you're doing it intentionally inside a car engine. Yeah.
So when I'm asked in the future in some class, whether it's this one or another one of yours, what is the second law of thermodynamics? When I say you can't break even, I'm going to be correct?
Well, you can't break even is the informal definition. It's just a way to remember it. It's just to remember that this is one physical law that's got a greater than sign instead of an equal sign, which is not typical. And there are other ways to describe it as well. We discussed specific examples of power. We did a linear mechanical system, a rotational system. We did an electrical system. In each case, you're just going to multiply an across variable by a through variable. Let me follow up on this one really quick, because somebody wanted to know how I turn that into heat. So I also know that V equals IR. So voltage equals current times resistance. I didn't draw my resistor here, but there it is. There's my resistance. If I take that equation and shove it in here, I get power equals I squared R. Now, what is that? What kind of energy is that?
Electrical?
It's electrical, but what it is, it's actually electrical energy being turned into thermal energy. You hear a lot of times, like, Montana's got this problem because it's so big, coal strip's way over there, electrons have to, flow all the way through these. It's just turning into heat. That's the loss. If there were no resistance, if you had superconductors, some metal that was better than copper, R would be 0, and there would be no power loss. That IR squared is just called Joule heating. So back in 1850, James Joule stood up and was telling everyone, heat is energy, heat is energy. It's like, what the heck are you talking about? But as it turned out, he was right, and this is just one example. If you stick, and we did this a few years ago, we just had somebody pedaling on a little bike on a generator, got a coil on a toaster oven hot, stuck it in a beaker, and the water started boiling. So we turned mechanical energy into thermal energy. That's all it is. So another example of the first law. And I'll just write it one more time here. V is voltage, and I is current. And this is just obviously just measured in volts and measured in amps. And then we went through these as well. So in this case, this is a fluid system. And let's just break it down into building energy efficiency. This would be a boiler, right? You might have a boiler in your house with heating, either radiant heat or little radiators. What's this one? If you're pumping air, what's that called?
Forced hot air.
Forced hot air. It's usually called a furnace. Yeah. And the distinction here is that this is actually mechanical energy flowing that we're talking about, and this is thermal. Both types of energy, and again, if you think you're missing some energy somewhere, just go back and check. It's going to be one of these forms. We haven't talked about chemical in much detail. That's a little trickier to write out in a simple way. The battery itself is an example, but okay. So hopefully that ties in different types of power. You know, it's all around us, but at the end of the day, it's just power. Multiply power by time, then you got energy. Okay, 30 minutes, perfect. Take a break, and we'll be right back.